Hello! Okay, here's our student view for conservation of angular momentum Edpuzzle.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 96. It's on the conservation of angular momentum.
Oh, and here's our first comment. Well, first requirement is a comment with an image. Perfect!
Now, how is angular momentum different from linear momentum? Remember, angular momentum is due to rotation. And you might think to yourself, why does the Earth continue to rotate? It's due to the conservation of angular momentum. It still maintains some of that angular momentum from the formation of the solar system. It's gradually slowing down, and it'll eventually stop, but it's not something that we have to worry about. So conservation of angular momentum will always be maintained as long as we have no net external torque acting on an object or acting on the system itself.
Remember that torque is just force when we are using rotational type problems.
So that was my audio over. I know it's at the same time as the review question, but I felt that this review question is more to just make sure they're paying attention and get them thinking rather than actually trying to test them. And right here it does show, because I went through previously and answered these, so it is showing what my answers were on this. Okay, so that's our first question, and it's a free response.
Now, unlike linear momentum, we can calculate angular momentum in one of two ways. If it's a point object in rotation, then our angular momentum is equal to the radius times the linear momentum of the object. So how fast it's going in this direction times its mass. If we've got an extended object, we use a different equation. If we're an extended object, the angular momentum is equal to the moment of inertia, so that's how much material we have and how far it's spread out from the center, times the angular velocity of the object.
All right, now here we have our multiple choice question, which I personally like this last option the best, but apparently it wasn't correct.
But in both cases, as long as there's no net external torque acting on it, the angular momentum before equals the angular momentum we have after. Now again, there are analogs for linear momentum. Remember, in linear momentum, during a collision like this, the momentum is simply transferred between the two. Now in linear momentum equals mass times the velocity of the object. But we have analogs when we're talking about angular momentum. So if we've got a rotating disk like this, how do we calculate its angular momentum? Well, our equation is L equals I times omega. In other words,
All right, so making sure we're paying attention and we're thinking critically. So the I in the equation for angular momentum is the mass of the object, which is false. It should be the moment of inertia. And then the W should be angular velocity. Yay.
Angular momentum equals the moment of inertia times the angular velocity. Let's say we have a point object like this in rotation. Then we're going to use a different equation. Now L equals RP, where R equals the radius, the distance from the center, and then this is going to be the linear momentum. It's the linear momentum we were talking about just a second ago. So that's going to be a product of the mass times the velocity.
All right, so that is the end of our video. So if we go back, we can see here, since we've got the allow skipping right here, we have turned on prevent skipping. We can see how many have completed it over here. And in our progress over here, we are able to export. And that saves how everybody's doing. Oh, look, it's me. And I'm just going to double check that that was everything I was supposed to say. Yep. Bye.